Welcome back. This is r2con 2021. This is the second day of the conference. I hope that everyone enjoyed yesterday. It was a training day, but this time we have so many presentations. And we'll begin the day speaking with Murphy. So welcome, Alex Sule. He will be talking about the R2 Freedom, making some demos and examples showing how to use mainly for iOS and Android application analysis. So, hope you enjoy. Murphy, that's your turn.
And I will present you an Frida workshop. It's more like a talk, but the idea is just to make it practical. So just to understand different use cases using Frida in mobile environments, in iOS and in Android. So enjoy. So just a brief overview about who I am. My name is Alex, I'm security researcher at AttackIQ, and I'm considered a mobile enthusiastic, especially in iOS, but as well in Android. And I'm a Frida trainer as well. We did some trainers related to Frida in past r2cons this year as well. And just you have my Twitter handle and my GitHub if you want to just get more information. So this talk, the idea is just to know more about Frida, just explaining what is around different commands, old commands and new commands related to Frida. So we are going to show as well the new things that we have. And we are going to explain as well how to develop and to automate processes using Frida, using the plugins and how to develop the plugins from scratch. So it's just an introductory presentation, and the idea as well is just to see different practical examples how to use Frida in different environments. And we are going to show different examples in iOS and others as well in Android. And just at the end, we have some surprise to show that we will see. So, what is Frida? For those that already don't know it already. On one side, Radar2, that all people here, we already know what it is. And we have in the other side, Frida, that you know that it's just the two walls. With Radar, we have the static wall, just analyzing binaries, analyzing data structures, and so on. And then we have the more dynamic wall using Frida in different environments, in iOS, Android, Windows, Linux. And well, you know that you can automate a lot of processes using Frida commands, and as you already know, or should already know, Frida is based mainly in JavaScript. So why not to put the two walls together, having the power of the static analysis that we have in Radar and all the poorness that Frida has in the dynamic wall. And this is quite powerful, especially in mobile environments, because Frida works pretty well in Android and in iOS, and allows us to just analyze all the information, all the applications into the memory and just get it all the information from memory and just get it into our radar2 session and just get all the features that we have in radar, as all the analysis algorithms, all the flags, and how to, for example, print all the disassembly, or for a good example as well is how to use r2frida to print the disassembly from memory using r2 Ghidra as well. So it's just a powerful tool as it in our radar wall in that case. So how it's implemented is just we have in one side radar that it's installed locally and it's written in C. If you didn't do it, just watch the talk yesterday that Pancake did related to how to develop plugins in Radar 2, and you will see how it looks like. And then we have the IO plugin that it communicates with a Frida agent that it's written in JavaScript, and that's the code that it's then injected into the applications through the Frida server. And that's the way how it works and how it's implemented. And the idea is just to invoke from Radar the Radar r2frida plugin. The idea is just to use the handler Frida // and that kind of URL. It's just what we use to invoke the r2frida commands from the Radar session. So just from the beginning, how to install r2frida, quite easy. So just if we use r2pm, just r2pm minus C, it's just to clean previous installations. If we want just to upgrade the installation using a newer version of r2frida, and then with minus I we install the plugin and just compile the agent as well. And this is if we want to use it from a user perspective. However, if we want to develop new features in r2frida and we want to contribute to the project, the best way to install it is just using make user install. What it does is just create a symlink to the project installation, and then we can just modify the project and just execute in make. We are going to use the updated version in that case. So just how it works is just in that case it's mainly oriented to mobile environments, and the only thing that we need now is just we have different mobile environments, an Android and an iOS environment with Frida installed inside the devices, and then we have connected the devices into our computers using a USB, and then we are going to invoke r2frida through the USB. In that case, just to identify the different devices that we have connected in our laptop, we are going to use the r2 Frida, and with the USB and two slashes, it's just going to print the different devices that we already have. And then if we want to connect to a specific device, we are going to put the device into the two slashes, as we can see in the second dot. We have different ways to interact with an application with r2frida. We can attach to a running process that it's just we can use to attach to the process the PID or the application name, or we can just run the application again and just we can spawn the application or we can launch the application. What's the difference between them? It's quite easy. The difference is that if we spawn the application is going to be paused at the beginning of the application, allow us to introduce all the Frida hooks that we want at the beginning of the application running, and then continue the execution of the application. That is what we get with the spawn. However, with launch, what we get is just automatically continues the application, so it's just running the application, and the application is just continuing to run in that case. So here we have different examples, and just with the command with the two dots dc command is just as explained before, just what we need to execute to continue the execution of the application in that case, just to resume the application. So something new that we have to consider from previous years is that the counter slash command, it's been deprecated, and now we have to use the colon command or the equal and exclamation mark command as a r2con handlers in that case. And just a quick way to identify all the commands that we have in the r2con wall is just with the colon and the question mark. We are going to get all the commands and the help and how to execute them. And in this talk, we are going to see some of them. So just to begin, the first thing that we should do in an application is just to get basic information from the application. So in that case, this is an iOS application, and what we get with the command I, in that case, is just for the bundle application that we are executing. In that case is demo Objective-C app, and as well we have the home directory, the temp directory, and the bundle directory, that are the directories that the application is using inside the iOS device. And this is a good way just to start to have, for example, what architecture we are analyzing, if we are working in 32 bits or in 64 bits, and this kind of information that can help us to understand the environment. In that case, one new thing that we have as well is just with this command, we can detect if the application has been compiled using Swift or only Objective-C. In that case, it's using the Objective-C environment. So we have some basics commands here to understand. The first thing is just to send an alert to the application. It's just with the first command, just with the E command in uppercase, and then the title, and then the message. And this is going to create a new alert in our iOS application. This is supported in iOS only for the moment. And this is just a good beginning to understand at least how it works, and just to check that it's working as expected. Then we have different r2con commands, native r2con commands that we are going to see right now. However, with r2con we can work as well with Frida scripts, or with Frida snippets even. So we can just create our Frida scripts or our Frida code snippet, and using r2con this code can be executed using the eval command if it's just a Frida snippet, or just with the colon dot and just the path to the script, we are going to execute this Frida script in that case. And something to have into account, to take into account for the r2con wall as well, it's just we are getting the powerness of radar as well, and all the commands that ends with a J are getting the output with JSON, or if it's ending with an asterisk at the end, it's returning the output as r2 commands. And this is quite useful if we want to, for example, update our r2 session with the new information get from Frida. And this is quite useful. We are going to see it in a couple of minutes. And it's, as you see just at the bottom of the slide, it's just printing the commands, and this with this dot it's just quite useful. So now we are going to get more information from the application, and we can get library information, the import information, or the exports, all the symbols. And the difference is just with changing the second character with an L, an I, an S, or an E, an uppercase E in that case. And this is quite useful because what we are going to do is just get this information, load it into the r2 session, and then just use it for our analysis, our deeper analysis. This is quite helpful if we want to do this like automatically. That is, with the init command, we can just any analysis. So just getting deeper, we are talking about iOS applications, but it's working as well for Android applications, but it's quite simple. In that case, what we want is just get the classes information, and this information can be imported into the r2 session. We are going to see this in detail in an example right now. So I'm going to just explain it maybe better in the example. And this is quite useful because it's a good way to access to the file system of our devices. It's only we only have support for the moment for iOS, but it's quite useful to mount the remote file system, in that case for our iOS, in our r2 session, and we can navigate through it, and even we can just download files from our iOS device without using, in that case, SSH. So it's just only using r2 Frida, we are able to access to the file system of the application and get the files from it. So we can just get the infopilis file to just analyze the information for the application, or all the information, the sensitive information that any application can generate into their container can be downloaded only using this command. That is just initializing the session with init, and then just with ms, you are going to have like a shell where you can just navigate through all the folders, and then just with get, you can download all the files that you want. So we are going to see an example about how to analyze an iOS method using r2 Frida, and we are going to put in practice all the commands that I just explained. So what we have here is just, I have an iPhone with an application. It's a custom application that I've developed for demo purposes, and then we have a shell that we are going to launch the application. As I told you, we are going to use, in that case, launch to avoid to resume the application. r2 Frida is going to resume the application automatically. We're going to connect to the device using the USB. We can put a device here if we want, a device ID, a device ID, or if we don't put any device, it's just getting the one connected by default. And if we don't know the name of the application, just with 2 slashes r2con is going to print all the applications that we have installed in our device. So I'm going to execute the application. As you saw, the application just rerun it, and then we are going to change some options, but it's quite useful to improve the analysis of, in that case, for iOS. And then we are going to execute init. So just automatically it's sticking to the entry point. The libraries have been already loaded, and if I just execute this command, we are going to see all the imports from the application. And if I put the star at the end, are printed, as I said, as r2 commands. So a good way to import this information into our session as flags is just put it a dot at the beginning, and we can do the same for the exports. So now the next step, now we have the R2 session with the imports and the export information loaded into current session, and now we are going to see the different classes that we have in the application. As you can see, we have a lot of classes because we are printing the classes implemented by the application and all the classes imported by the application as well. So a good way to just check the classes implemented by the application is just using this command, that is icwdn, and just filtering by the name of the application. So we can see here are the classes implemented by this application. So now we are going to see the methods implemented by this class, that are these ones in that case. And another useful command is just, if you use the star at the end of this command, you're going to see the information as flags. So this information can be as well imported into our R2 session, and this is quite useful if now we want to just use the seek command using the flags to move around the application and around the methods using the names instead of just pointers. So we are going to move to the isJailbroken method, analyze the function, and with PDG we are going to print the disassembly using r2 Ghidra. This is quite powerful because what we are doing right now is just getting the disassembly from memory and just decompiling the information directly from memory. This is quite useful in iOS because, as you know, iOS applications has a DRM implemented that if we want to analyze the binary, we need to decrypt the binary first. However, if we are using r2, we are working directly in memory, so it's not needed to decrypt the process because everything is already decrypted in memory. So here we have the method that it just here. However, Okay. Here in that case, we can see that we have two different functions that we don't know what it is. However, if we print this pointer, we can see that this is a string referencing to APT, that it's just a path typically used for jailbreak detections. So we are going to check what are these functions and how to analyze it. So we are going to just analyze the function using the SL command. And just let me check here. Okay, I forgot to just. This command is just to improve the analysis and just executing AC, AF, and AA. Exactly. So we are going to use SL, just different analyzing the calls and analyzing the function. And if we print it again, yeah, here we go. We have resolved the calls to this function, so we already know that this function that before. So this access function is using this pointer, that if we print what is this pointing, it's just a string to see the application. What we have here is just a very simple way to check if a device is jailbroken, checking if this file exists using access, and if not exists, it's just creating another checking using DLSIM. The DLSIM is just a function for iOS used to resolve resolve functions. And what we are resolving is the string stored in that address, that is the LStat. So what we are doing is just executing LStat, as we can see here, related to what it's stored here. That is, so we are using LStat to check if this file exists into the system, and if it exists, it's just showing that the device is jailbroken, and if not, so it's just checking that it. So just to some different things that we can do as well. This is from the R2 wall, because we are analyzing the function using radar and getting information using Frida. But we can do more things in the dynamic wall using R2 Frida. So one example is just we can call methods. So as we saw, we have the main controller, and we have different methods, and here we have a method that is changing the background of the application, or at least it seems to. So something that we can do is just execute AFS. Sorry, because I forgot to put the class name. Just to check what is the method signature. We can see that we have a pointer, another pointer, and an integer. This integer is referenced to the first parameter of the method, and these ones are referenced to, this is referencing the class name, and this is referencing the method name. This is how it works in the iOS world, that always the first two arguments, the first one is a reference to the class, and the second one is a reference to the method name. So just executing the exo, like the exo is a method to call Objective-C methods. We can see how we can get this method and call it, and just change the background, as you can see right now. Just sending an integer, we are updating the application color. So it's a good way and an easy way to interact with application methods, only knowing the class name and the method name. And just to understand the parameters, we can use the EFS r2con command to just get the function signature and just interact from it. Cool. Let's continue with the slides. So slides, this is the DXO command that we have already used to just interact with the application, and the EFS command, that the function signature, and just to understand how the application is implemented. So from the dynamic wall, we can now call, we can call functions, we can interact with the functions. However, we need as well to understand and to monitor the applications itself. So a good way to understand when a specific function is called, or when a specific class it's been used or not, a good way is just to tracing the code. And with r2frida, we have DTF, that with DTF we can trace function calls, and as well we can define as an argument different parameters to just depending on the function signature, just to print not only when the function is called, but to print as well the arguments that the method call is using in that case. So we can use DTF if we want to interact directly with pointers and with the arguments, or we can use DTR if what we want is just to print the registers used when the function call is called. And this is quite useful when we are interacting with system calls and with low-level functions, that it's just passing all the information in the registers, and it's a good way to just quickly understand how all the information is passed and what kind of information is passed. Here we have the DTF and the DTR example of the same function. As you can see, the difference is that with DTF you are seeing the output as an argument, and with DTR you are seeing the output as registers, as x0, x1, x2, and so on. However, because of using ARM architectures, you are passing parameters using the registers. You can see this exactly the same information as you can see in the slide. And for iOS, I mean, to just use DTF or TTR or any tracing command, you need to use or a symbol name or a pointer to the function. However, in iOS, it's implemented like a helper, that is the Objective-C helper, that can allow us to resolve this information automatically. So we can trace Objective-C functions using Objective-C column, and then the class name, and then the method name. So we are going to see an easy example when to use DTF. As we already know, some applications are implementing certificate pinning to avoid to intercept the traffic of the application, and just to understand what kind of information it's just sent between the application and the servers. And there are a lot of different ways to just bypass the certificate pinning checks. However, an easy way is just, instead of having a proxy between the device and the server to get the communication, the HTTP requests and so on, instead of that, we can get directly the information of all the HTTP requests generated by the application directly from the method names, the method calls that it's been used. So yeah, I'm going to show you a quick example how to intercept communications of an application. That in that case it's an application that I know that it's implementing certificate pinning, so it's not easy to put a proxy like a burp or another proxy, because it's just detecting that the communication is being tampered and analyzed, and it's just blocking all the communications. So a good way and an easy way is just to monitor directly the functions, in that case the Objective-C functions that the application may use to communicate with the servers, and print all the information stored in the arguments, and with that we can monitor the URLs used in the different communications with applications, and even the content of the body of the request sent to the server. This is how it's been done. It's just using the DTF, the Objective-C handler, and then this is the class name, and this is the method name. I'm using just these characters just to just narrow the search and to avoid having conflicts with method names that can happen. And with these commands, what we are doing is just configuring the parameters. Is just a configuration of the agent. So we have different parameters that we are going to show just right now, and with that we get the information with JSON in JSON format, and we are not going to print the backtrace, because if not, it's just too much verbose, the output. So I'm just going to execute the script as it is. The application is triggered, it's launched, and now it's just printing all the requests done by the application. As you can see, the application is still working, so it's just getting the information itself, and we have all the URLs just here. For example, here we have another URL, and it's a good way to get as well vulnerabilities in a quick way. In that case, it seems like an API key that maybe it's just used for this application, and just we can get it only just executing the script and just analyzing all the communications just from it. Cool. Getting back to the presentation. So now we know how to interact with the methods into an application. We know how to monitor the method calls, so we know when a method it's been called or not. Now what we are going to do is just we are going to modify the behavior of the methods. How? So here we have different methods to modify the return value of the methods. And when this is useful, this is quite useful when we are working with security checks like anti-FRIDA checks, with anti-routing checks, or anti-jailbreak checks that are just functions making different checks into the system and then just returning true or false depending on if the application is jailbroken, if the device is jailbroken or not. So with these methods, we can just modify the return value of the functions quite easy, as you are going to see right now, and returning what we want. So we have if we are using a 0 or a 1 into the method, we are returning 0 or 1, or as it's the same, true or false. If we are using the def with the f at the end, it's calling the original method. Without the f, it's not calling the original method. So what we are doing is just substituting the function call, just returning the value without calling the original code. And with the f, we are actually executing the original code. And we can return an arbitrary integer or even a string if we want. So let's see a practical case using the AI just to bypass routing checks. So now I'm going to use an Android device. I'm just connecting the Android device. Yeah, you should see there already the Android device. And here I'm going to spawn the application. This application is just for testing purposes. It's just to check if the device is root or not. It's doing different checks, and it's a good way to identify which kind of checks your device is failing for typical anti-routing checks. So here I have different checks that I'm failing, even some native checks. So just let's analyze the application and see how to bypass all the checks. So in Android we have the command IC as well, just to analyze the classes implemented. And just to narrow the search, we are going to filter the results for root beer. That it's the package name of the application. So we have different classes. This is the main class. So we are going to copy and just print the methods implemented into this class. So we can see how are different checks already implemented. Checks so exist, so binary, read-write paths, magic binary. So there are different checks implemented using Java, and we are going to just bypass these checks using the DI command. So we are failing in those 4 because this one, as we can see in the name, it's native, so I'm pretty sure that it's not implemented in Java. And for example, the SUEXIST referencing the subbinary, or we have the read-write paths just right here that it's failing as well. So we need to just modify the return value of different functions that, as you have seen, are returning Boolean, mainly all of them. So the only thing that we just need is just executing the di command with 0 at the end, just returning false always, It doesn't matter the device, it doesn't matter the checks. And we remember that if we are executing with the F, we are calling the original methods. However, now we don't want that. So just return false, and that's it. For Android, we have a handler that is Java. It's not implemented in all the commands, but it's implemented in this one. And you can just have the package name, the class name, and the method name, and just do the same for all of them. Just let me copy this just to be quicker. Check for binary 0. Check for read write paths and Java. Check for Magis binary. And now we are going just to trigger again the checks. We can see that automatically when we are using the Java handler, r2con is adding Java traces into the application just to notify us that the method it's been called, and then it's been modified with 0. And as you can see, all the Java checks have been easily bypassed and quickly bypassed. So we are going to just bypass the native checks. How to do that? So the first thing is just we need to identify where the native checks are implemented. Normally, how in Android it's working with GNI. It's just we have like a stub implemented in Java, and then this stub is loading a library, and this library is implementing the code itself. So we are going to check the libraries, and just to narrow the search, we are going to filter by check, and here we have the library that is implementing all the logic of the native checks. So as you remember, with the start, we are going to load the library's information into the r2 session with the dot at the beginning, and now we can just jump to the library code. Once we are inside the library code, we can get all the imports and the export information from the library, import it into the r2 session, and we are going to see which exports has the library. So because the Java it's calling the function, the native function, using an export. So we have different exports, and this is maybe suspicious because of the name. And we are going to jump to this code. Okay. So now, what? I forgot. Yeah. Now, okay. So now we are going to analyze the function, using guessing as well to analyze the function, and just using r2con to print into this, to the compile the function. So it's triggering a little bit. And there we go. So we have the check root. It's doing different things. And as you can see, there are different function calls. So we can see, for example, let me check this function to see what is implementing. We are analyzing the function as well, and we are going to print the function. I don't know why it's not getting. Let me come back. To this one. So I don't know why it's not just praying for the demo gods, but should have we should see a reference to this method, that it's just a cross reference. I don't know why r2reader is not printed as expected, but we are going to move to this function and to analyze the function as well using gasil and er command, and we are going to print the disassembly. Okay. So this is another function that it's doing something with this function, storing in this variable, and depending of the value of this variable, it's just doing one thing or the other. So just to auto-name the functions after an analysis, this is a useful command with its AIN. So if we execute again the r2reader, either to Ghidra decompiling, we are renaming the function, so now it's quite easier to understand what the method is doing. So in that case, it's just calling the open of an argument, that it's just calling the open method of this argument, and depending of the value of the open, just what it's doing is just checking if some file is existing into the system or not. It's just printing a log or printing another log. So what it's printing, it's just, we can just print the values stored in the pointers. So we can see that what it's doing is just checking. It's an anti-routing checking, and it's just checking if a specific file is present into the system, and depending on if it's present or not, just returning a value or not, and printing a specific log for it. So just to bypass this, we can just get this method and bypass it. So here we have a script. I'm going to show you that it's just tracing the function just to check that it's been called, and then modifying the value. What it's doing, this method, it's just getting the exports and filtering by the exist, and then just getting the address in that way. So just double check This is the method that I'm just actually modifying and tracing. And if we call again the application, we can see all the different arguments that it's, so the different paths verified by the application. So SU in that case, another SU binary, different locations of the SU binary. As you can see, failsafe, blah blah blah. So all the different binaries are printed in the screen, so we can see the different paths checked by the application, and then how it's been bypassed just with the di0 command. Put it into the export function, that it's the one checking the files using the open syscall. Cool. So this is what we have already explained. We are going to talk about R2 plugins. So how to all what we did was just manually for analysis purposes and using small scripts. However, if we want to do something more complex, we need to do it as an R2 Frida plugin. So how it's working is just the plugin is implemented in JavaScript. The only thing that you have to consider is just to call the plugin register API to load the plugin to Frida, and then you can load the plugins using the dot at the beginning with the file name, and it just loading the plugins, and you can list all the plugins. So in this image, you can see an example of how to implement the typical hello world using an R2 Frida plugin. Here we have the code. It's quite simple and can be used even as a template, because you have at the beginning an array, and is where it's a hash where the commands are defined. Then we are calling the plugin register API called using as a parameter the commands structure to register the plugin, and then we have all the functions that are called when the command it's used. In that case, we have a function called hello that is being used by a command called hello as well. And as well, we have the plugin name that is used inside the plugin register API that is called hello as well. So just with this simple structure, we have a typical hello world in R2 Frida, just to have it as a good template to create your more complex plugins for R2 Frida. This is a simple example, just using the API resolver for Objective-C that it's implemented in the Frida API for iOS. And what we are doing here is just implemented the command find inside R2 Frida, just to look for different class names or method names depending on how the expression it's used as an argument. We have another example that is a Mako parser. Mako is the format of the iOS binaries, or Mac, it's the Apple world in that case. And what we are doing is just loading the plugin, and then with the star we are getting the output as rather commands, and these commands can be implemented as flags into the session. So it's a good way to have all the Mac parsed and having all the flags updated into your R2 Frida session quite easily. And here you have the code, it's bigger. However, you have the snippet to how to convert the output of a function to r2frida commands, that is just returning the string as it states in just here. So more complex examples of R2 plugins. We can here we have it's an example for iOS. It's just a URL schema fuzzer. It's just it's nothing new. It's something that it's been already implemented in Frida, and what I did is just get the code and import and just update it to Frida as an example. Let me show a video of a demo executing this r2frida script. Okay, here I'm attaching to the Springboard. I'm just importing the plugin and fuzzing the eCode URL schema, and just with the contact name 666, and then in the message it's what I'm putting as a fuzzing string, and then I'm just calling the application continuously, the URL schema, and just what I have to do is just wait to identify if the application crash, and if it crashes, just check what string just crashed the application and just analyze deeper from it. And this is a simple but useful example of a specific use case to use a r2frida command, a r2frida plugin, sorry, to implement something useful, to automate a complex process for your mobile apps analysis. And this is an example for iOS, but can be done for Android as well, using deep links. So this is another example. That this is the surprise of this talk, that I just reserve it for the end. And this is an iOS application decrypter. That as I told you before, you know that iOS applications are implementing a DRM to avoid to being analyzed, and you need to decrypt the application before put it into your radar session to analyze it statically. So to do that, there are a lot of different tools. However, I decided to implement the Mind using as a r2frida plugin, and it's just a small tool composed by a r2frida plugin and Python. A Python script that is using r2pipe to interact with the device, and it's only supporting 64-bit and something good for this that other tools maybe have not is you don't need SSH to put your SSH credentials to download the app bundle. So everything is done using Frida, and using as I told you before, it's using all the IO features to download all the content from the application. And what you can do is just downloading only the binary, or if you want to generate the IPA file, you're using the whole app bundle, you can do it as well with -i. So just to get it, the requirements, it's quite easy. It's just a jailbroken device, an iOS jailbroken device, rather to install in your local machine and Frida install in the device. And then to install it, you can just use pip install r2flush, or r2pm -ci r2flush, and with -l you're listing all the applications of the device and just putting the app bundle. Afterwards you are getting the application bundle and downloading the content as well from memory. In that case, the r2Freezer plugin, what it's doing is just analyzing the application, analyzing the structures in the applications, and just getting the decrypted portion of the code and just patching the binary in local. So just I have a video just to end, just a quick demonstration about how it works. So okay. Sorry. Yeah. I don't know why the video is not working. Let me check. Okay. I don't know if you can see well the video. However, it's just what you can see. It's just how the application is being downloaded and the IP is created. I'm going to upload the videos so you can check it afterwards. So just to finish, well, this is how it looks like. And just to finish, just say thanks to all the people that it's just helping to all these projects to continue. All the references, especially for the source code of the r2flush tool, for the plugins and the examples that I used during this talk, and different references and videos to learn more to the r2Freezer web. So yeah, now that's it. Thank you. Sorry for the video, and well, hope you enjoyed. Now it's yours, Pancake.
Thanks, Alex. We're gonna make a quick transition to the waiting scene, and then we'll start with a presentation from Captain Banana.
Hey yo, what's up? It's Banana Man. I hope you all had a great trip to Barcelona. Today I'm talking about the intersection of R2, Frida, mobile security and dildos. So I came across this pretty interesting product. It's called Satisfier and it's a dildo but with an app. So you can connect to it using Bluetooth and control it. And there are quite a few people using this app. It's mainly sold across Europe. And a main feature is that you can add friends in the app and allow them to control your Satisfier remotely. And I wanted to see if I can pose as any other user on the app and trick people into allowing me to control their devices. So I did all sorts of analysis on this app. I've decompiled it using CFR and did some static analysis. And I've used Burp to view the traffic of this app in combination with Frida and the universal third pinning bypass to actually see the traffic. Authentication is handled using JWTs in this app. And upon starting the app, it generates a JWT, and that's used to authenticate at the server as an anonymous user before logging in. And what's interesting is that this JWT actually has to be signed in order to be accepted by the server. And the key used during signing is hard-coded in a native library. So as you can see, there's a function called getReleaseKey. It's originating from this library. And the key is being used in this call to sign with. And that's basically the initial authentication. Now, if you look at authentication, you see quite some difference. The first one being the subject being set to Satisfier for unauthenticated users, and the subject being the username for authenticated users. Another difference is that the auth role is set to anonymous client for anonymous users, and upon logging in you receive the role user. And authenticated users also have another attribute in their JWTs called user ID. So I wanted to extract this signing key and use it to make my own JWTs for any other user. And there are quite a few ways to extract this key. The simplest one being just using R2, opening the shared library and disassembling the getReleaseKey function. And as you can see, the key is embedded as a string constant. Another way would be to use Frida. A simple technique is just creating a new instance of this JWT token builder class and just calling getReleaseKey and printing the result. And another option is to actually find the exported functions in the native library and adding an onLeave hook to just print the return value of this specific function. And of course, you can just use R2 Frida. Here I'm attaching to a running Android app, and I'm listing the available modules. The shared library that I'm interested in is called libnative-lib. So I'm adding a trace point at a specific location for the register x1, and I'm triggering JWT creation, and as you can see, the secret is being printed. So to actually use this key to forge a JWT, you could use your own code, but I've decided to just let the Android app do the heavy lifting for me. So I've used Frida to overload two specific functions. The first one being claim, which is being used to add the information which user is holding this JWT. And I'm changing it in a way that allows me to add a specific user ID to this JWT. And another one being the set subject that allows me to set the subject as the specific username that I want to be. So then, if we want to pose as any user, we need the user ID. And luckily, there's an API call you can use to just search for a specific user using the username, and the endpoint just returns the ID. So the ID is public and it's not secret. And then we can use the generated JWT to, for example, change the account description, which is like a status you can set. And here I'm using the put request, my generated JWT, and I'm setting the description to hacked. And the API says, okay, that's fine. And then I've effectively changed the description of another user that I don't even have a password for. So which means it is a server-side issue that has to be mitigated on the server side. So JWTs for authenticated users should be validated using another key that's secret. And the app doesn't have to be changed. But it's always a strange thing to do, to add the signing key to the app that's accessible for any user. So what did we actually learn? There are many ways to use R2 and Frida to analyze apps, and I found R2 Frida to work really well when remersing complex applications. So yeah, that's it. I've also published a blog post for this if you want to read it, and I guess the issue was patched by the vendor after some back and forth. So yeah, that's it. Thanks for having me.
I'd like to talk about how Chain Framework integrate with R2, and mostly I will focus on the details I didn't cover in my last HITB talk. If you didn't watch that talk, never mind. I will do a fast recap. So first of all, the recap in the last HTV AMS 2021, I did the talk on when chilling meets Radar 2 and how we implement our symbolic execution based on Radar 2 and the chilling framework. And today I'd like to focus on some interesting details and mostly the black magic behind the whole thing. So fast recap of chilling framework. Chilling provides almost the best dynamic instrumentation experience. For example, it's system simulation and you have flexible hook and snapshot and have full control of the sandbox. And so what's next? So we think for a long time what's the next of chilling framework, and our answer is we have to expand the ability to analyze both dynamic analysis and static analysis, and the best solution is to R2 since it's free. The free software is open source and it's the best alternative, not anti-pattern. So our first demo is symbolic execution. So about R2, R2 is a sweet snap of the reverse engineering, but it also has almost the steepest learning curve. You have to learn different commands, and sometimes the source is your best friends. As often the case, I have to read the parser to know which command I need. But you could find almost everything, yes, everything you need for security analysis. For example, you want to disassemble some instructions, you want to show the control flow, and you could debug. And it also has tons of utilities. For example, the question mark is my favorite, And what we chilling team really focus on is the ESL, the Evaluable Strings Intermediate Language, and it uses reverse polish notation and designed for interpretation and suitable for symbolic execution. So first of all, R2 is written in C language, and the chilling is written in Python language, so there needs a bridge. And the existing solution is r2 pipe and r2long. r2 pipe was the only available Python binding at that time, but it requires rather to be installed system-wide, and we hope to minimize the chilling installation to pip install. So we don't want user to execute various commands to install a dependency. So the r2 pipe is not suitable for the direct use. r2long is the other way. It's running a Python interpreter in R2, and it seems good, but we expect to run standalone, and it's still system-wide R2 installation is required. So I decided to reinvent the view. So I wrote a brand new Python binding for R2 bar. So how it works, R2 headers is clean enough to do auto generation for almost every API is marked with R API, and the bindings are generated automatically with ctype slip and the GitHub CI. So in this talk, I would cover the detail of this part. So go next. So actually, how it works, we have C header from Radar 2, and we expect Python C type bindings, and the 2 is C type lib 2. It's backend by libclone, and it parses the C header and up to the AST and produce the Python script from the AST. But it's not actually maintained. It has many bugs, and for example, there are many issues I raised to fix some bugs which prevent the generation, and that's all. So with the bugs fixed, we could generate the Python bindings seamlessly. No. So let's see the real black magic. First off, RU2. Unlike other R2 modules, it is managed by multiple headers. There are no R2 API in the header file. As you can see, it includes RU2, REvent, various subheaders. But so ctype won't generate symbols in included headers. Or for example, if it do generate symbols in the included headers, the headers like stdio and stlib will be also generated. So ctype won't generate symbols in included headers. So what's my solution? I do the expansion manually, like the standard C preprocessor, and I apply ctype on the expanded header. For example, here as you can see, I generated a brand new header ru2 gen.h. It is composed of all these headers. Just copy their content to these headers by the sequence, and get this big file and generate all symbols from this file. So that's still enough. We still have more black magic. So after we generate the bindings, we have to put everything together. Unfortunately, ctype is designed to output a single script. For example, you have a header, you have a source file. It just generates that script, and you can only use with that script. But we would like a library. We want just for example, you import libbar and you get everything. So we have to try to put everything together. So my solution is to mangle output by regular expression. Yeah, it's 30. I know it's 30 indeed, but it works. Basically, this is the only way I could think about that could solve the problem, and it gives each R module a separate namespace, and I remove the local path generated. For example, my local path generated and make it relative. And I write a wrapper to use the relative path to load all R libs. So the last black magic, is Mason. Oh, you may not imagine what's the problem with Mason. So first of all, we would like the cross-platform, so I choose Mason, but it has very critical bug on macOS. Here I give a link. But basically, in summary, you can't use relative paths to refer dynamically on on Mason-built libraries. So it's really frustrating. I tried many times, and finally I found it's a bug of Mason. So what's my solution? And another black magic. I parse the libraries. It's macro files, and rewrite the dialoader path. So it's the last black magic, and put all these black magic together. What you get? A working R2D bar, a passive bindings. So that's R2D bar. And next, I will cover some details about how the symbolic execution implemented. So I skip the concept and demo. If you are unfamiliar with this part, you could go to the HITB YouTube channel and saw my demo and some concept introduction. So for today's talk, I just start from the difficulties so I could introduce the details. So first of all, the implementation is much complex than expected. R2 itself doesn't have memory rewrite implemented, so we have to do it our own. And also we can't use R2 registers implementation due to we have to store symbolic values, and as a result we did a full re-implementation of ESL. No, not all. R2 is still responsible for the design, but the interpreter is implemented by our own. And it may become another emulation engine to replace Unicorn. I will discuss this later. And the symbolic execution is never a silver bullet. Sometimes it's really slow since you have to keep every state immutable. Also, I know there are many things to optimize, but in theory you have to keep each state, and the state would be exploded for a complex function and make it acceptable slow. So let's see some details. First off, the memory. So why would I like to re-implement the memory? Since we would like the memory that holds symbolic values, and it should support full clone since the memory, a memory object or a memory of a state should be immutable, and it also should support a memory map and a map, and the implementation. So the memory itself is managed by segments. So you couldn't just allocate a very long array and allow user to write values. You have to use segments. Every time user writes to an address, you allocate a new segment, just like the page tables. But I implement a simpler version. So it's managed by segments. Every time user writes to an address, you create a segment and insert to current segment array. And it's really complex than expected. For example, when I insert a segment, I have to check the overlap segment and merge segment or delete some existing segment and replace it with a new one. So it's really complex. And the second implementation is the register implementation. Again, the reason is that we would like the register to hold the symbolic values. And it also should support full clone since we need an immutable copy for each state. But fortunately, it's much simpler than memory. And most importantly, we do a full implementation of the ESL interpreter. So first of all, since we have implemented the memory and registers, so it's impossible to use R2 implementation. And in our implementation, the most important part is how we handle symbolic values when we encounter a branch. When we here is the code snippet. When we encounter a branch, for example, if here we add the conditions to the we add the condition. For example, here source doesn't equal to 0, and then after we interpret this macro code, we search the possible PC. For example, we just add the condition of the true. In this function, we could search whether it could be false or other branch. So in this case, ESL solved really a nice reference, and I learned many symbolic execution knowledge from ESL solve, and still we do our unique optimization on our side. So for future, you may ask, wow, you gave the talk on symbolic execution 3 months ago. Why you still don't make it public or open source? So basically, the symbolic execution is still in heavy development, and what I was doing is Unicore 2. Yes. So in order to release the symbolic execution, we are waiting for the Unicore 2 to be released, and then we may have the engine module, and we can introduce ESL as a new engine, and then we can implement the symbolic execution based on the ESL, and then we have a better collection of the extension, and you could and for the future steps. Sorry, I have a typo here. This is the future steps. Firstly, we just release the EVM, I'm working on Unicore 2. Yeah, it's a brand new version of Unicore 2. Now, not only I add some, not only it is bumped to QEMU higher QEMU 5. Unicore originally is based on QEMU 2, which is quite old, and Unicore 2 is based on QEMU 5, and also I add very a lot of exciting features, and also yeah, our chilling team recently is working on some secret projects based on UC2 and its new features. And then after we release UC2 and then release this secret project, and we are going to introduce ESL as an alternative engine to Unicore, I mean, and after that we could introduce the rest of R2 components to for example implement symbolic execution and the various stack analysis. So that's all the future steps. And last for credits, so first off, the Radar 2 for the next project, and Synaptically for R2 Libar implementation is also for the reference, and Anchor for the design reference, these three for the excellent solver, and Pancake for the template help. So that's all. Thank you.